This is a brief review video about Lyapunov's functions. I want to remind you again, as I wrote in a couple of announcements and a couple of messages, that Lyapunov's functions will not be covered in the final. Sorry about that, because it would be too hard. Lyapunov's functions are always built on a case-by-case basis, and it would be sometimes up to luck to find the right one. So what is a Lyapunov's function? The idea is that when you're we want to have a physical representation of what a node is. What? We want to have a physical representation of how a physical system behaves. When we're thinking about I am sorry, I have a hiccup and I'm not able to handle it at the moment. Think about a little ball subjected to gravity walking on a surface. If you know the shape of the surface, you don't have to know the solution of the trajectory. You know that the ball that you're talking about is going to go towards concave points at the bottom of bowl-shaped areas. Tips of mountains, for example, are critical points, but they're unstable. So as soon as you move away from that, the ball will fall down. We want to find something a bit more abstract that corresponds to the shape of the surface in a physical system. And what we have is Lyapunov's functions. What we want is finding something, a function v. So let's set up the situation first. We have x dot equals f of xy and y dot equals g of xy. And we want to find a function v such that if xt, yt is a solution to our system, it goes downwards on v. So we think of v as the surface on which our mass particle is moving on, and we want to find v such that our mass particle always moves downwards. Sometimes it's not possible because it just simply does not exist. Sometimes it is. Sometimes we find something that is, it always moves downwards, but the critical point is not at the bottom of a valley. So our solution goes just next to the critical point and keeps going down. I'm sorry for the hiccup. And so forth. The idea of trajectory always moving in a certain direction with respect to v is encapsulated by v dot. V dot is called the derivative of v with respect to the system. What is the idea? Is that we're calculating v along a trajectory. So along xt, sorry about that, xt, yt, where xt, yt is a solution of our ODE, and we take the derivative of this with respect to time. V itself does not depend on time, but because it depends on x and on y, and x depends on time and y depends on time, so v as a function of xt and yt depends on time. If we do the calculation, we notice that this becomes partial derivative with respect to x of v computed at xt, yt times the derivative of x. But the derivative of x comes from our system. This is f xy. And in a similar way, you have the derivative with respect to y of v computed at xt yt times g of xy. Now these are all things we can compute. We can compute the partial derivatives of v, and we know f and g. So we can compute v dot. If v dot has a constant sign, that means that along a trajectory, v constantly decreases or constantly increases. So we are able to, if we can find a v such that v dot has a constant sign everywhere except at a critical point, we're able to say that trajectories either always go downwards on the surface v or always go upwards on the surface v. So let's think of it in a more graphical way. We have our critical point here, and we have v that starts, wait, this is not a great plan. This is also not great. That looks like this. So our critical point is at the bottom of a ball. We can have two possible situations. So this is v. If we know that v dot is positive or equal to 0 at all points, and in particular is v dot is equal to 0 only at the critical point, then what we need to have is that our trajectories are constantly growing in v. So if this is a surface, you need to, wherever you start, you have to start climbing at it. That means that you're moving away from the critical point. What happens is if v dot is equal to 0 at all times? Well, it means that if you start somewhere on the v surface, you have to stay at the same height at all times. So you have to circle around in a certain sense, and you cannot move from here. You might go in one direction, the other, or stay put. Well, it's not a critical point, so you have to move in either one or the other direction, but you're not going away or towards a critical point. So v dot equal to 0 gives you periodic orbits. Gives you possibly periodic orbits, but definitely stability, but not asymptotic stability. If you think in the sense of stability or instability, when we had v dot positive, then we had instability. Things were moving away. What happens when v dot is smaller or equal to 0? Then what it means, let me take a new color, is that if you start here at any point on the surface v, then you have to go down. And the only way down at some point is only towards the critical point, because the critical point is at the bottom. So if we have also v dot equal to 0 only at critical point, then we have asymptotic stability. If we have the opposite scenario, so the critical point is at the top of a ball, then everything flips around. So if v dot is positive and equal to 0 only at critical point, that means you're climbing up. So this is the green case. That means that the critical point is stable and asymptotically stable. If v dot is equal to 0, we have the same situation as before. We have stability and potential periodic orbits, but not asymptotic stability. And if v dot is negative, and equal to 0 only at critical point. Notice that it has to be 0 at the critical point because we have f and g multiplying the two terms of v dot. So it has to be 0 at the critical point. We just are interested in the sign everywhere else. So if v dot is negative, this is our red case, that means if we start somewhere, we have to move away. So this is instability. What happens when v doesn't have a clear sign? So we have the critical point, and v in some direction is negative, and in some direction is positive. Yes. Something like this. Well then, whatever the sign of v dot, what it means is that you're passing through. So if this is v, and v dot tells you that you're constantly going down, well, you pass around the critical point and then you move downwards. If v dot is positive, well, you move upwards in v, you pass by the critical point and you keep on moving. So if v doesn't have a clear sign, but v dot has, then you have instability. Sometimes you have v with a clear sign, but v dot without a clear sign. So v dot, it's in some places positive and in some places negative. That tells you nothing. So you have to construct a Lyapunov function such that v dot has a clear sign. If you can find v dot having a clear sign, either always positive or always negative, then you can use that as a Lyapunov function. If you cannot find it, it might not exist, so you might not have information through the Lyapunov method. Sorry for all the hiccups included in this video. I hope it has been clear anyway.